A very good morning to my dear panels. My name is Ruttiran ANBUALAGAN. My entry number is B0918100371. I would like to express my heartfelt gratitude to everyone who contributed to my successful completion of this report. My heartfelt thanks goes to my supervisor, TS Dr. AZAZI bin NGATIMAN, for guiding and encouraging me from the start. Okay, let's go to the research title. My title of this research is Faulty Gear Vibration, Diagnostic and Monitoring. In engineering, vibration is a crucial topic to examine since it occurs as a result of movement. The oscillatory movement exhibits features such as frequency, velocity, amplitude, displacement, acceleration, phase, and period. Physical vibration components include mass, stiffness, damping, which are all comparable to acceleration, amplitude, velocity, displacement, and respectively. Vibration is classified into three types: forced vibration, free vibration, and damped and undamped vibration. Statistical signal process is an approach that treats signal as stochastic processes and uses their statistical features to perform signals. In signal processing applications, statistical techniques are widely used. For example, when you photograph an image, you can map the probability distribution of noise and build technique using the image model to reduce noise. Problem statement. Gear are the major element of rotating equipment and may be classified into three types: tooth, manufacturing method, and material. To identify a defective gear, it is nearly difficult to do so using simple human gears. Out of position, fractured gears are all frequent gear defects that must be detected prior to failure. When all the machinery parts and components are fully operational, noise and vibration may occur. In the long term, these conditions may have a direct effect on the regular operation of all of the equipment. Additionally, not everyone has access to appropriate equipment or machinery capable of tracking down a malfunctioning piece of equipment in a timely manner. Research objective: to measure the vibration of normal and fault gear using accelerometer sensor. To analyze the vibration data of the gear via various of vibration statistical analysis method. Number 3, to verify an analysis done by R-square and data distribution method via ZFRAC. Scope of research. The following are the scope of research in these faulty gear vibration diagnostics and monitoring. Helical gear and spur gear are utilized in this research. Two different gear situations were chosen for this research: a regular gear and a malfunctioning gear, in order to compare the outcomes between them. Create a simulation model in MATLAB. Conduct a vibration analysis utilizing the vibration signal analysis VSA, the fast Fourier transform FFT, and time domain, the root mean square, and ZFRAC coefficient. Literature review on conducting monitoring and diagnostic fault detection, signal processing, and vibration analysis will be discussed in this chapter. These studies reference come from journal, books, and in the internet. The goal of going over various articles about faults in spur gear and helical gear is to obtain a better grasp to how to conduct faulty gear vibration diagnostic and monitoring. Gearbox fault diagnosis under different operation conditions based on time sequence average and assemble empirical mode decomposition. Author by Lian Guan, Yimin Shou, Franjigua, and Bruno Fazenda and Enderbal. In this paper, a new method is proposed by combining assemble imperial mode decomposition (EEMD), which order tracking techniques to analyze the vibration signals from a two-stages helical gearbox. The method improves EEMD results in that it overcomes the potential differentiations and achieve better order spectrum representation for fault diagnosis. Based on that analysis, a diagnostic feature is designed based on the order spectra of extracted IFMS for detection and separation of gearbox faults. Experimental results show these features is sensitive to different fault severities and robust to influence from operation conditions and remote sensor location. Second, vibration signal based fault detection for rotating machines. Geoffrey Lane McDonald's 2011. The aim of this thesis is to improve upon existing vibration signal methods for detecting rotating machines fault in gear, bearing and rotors. Faults manifesting in impulse like vibration signals are focused on, which includes faults as a rotor to stator rubbing, bearing inner outer race failure and gear faults. A dynamic model to predict modulation sidebands of a planetary gear set having manufacturing errors, authored by Inopolat Makaraman A. 2011. A non-linear time-varying dynamic model is proposed to predict modulation sidebands of planetary gear sets. This discrete dynamic model includes periodically time-varying gear mesh stiffnesses and the non-linearities associated with tooth separations. The model uses from a gear mesh interface excitations that are in amplitude and frequency modulated due to a class of gear manufacturing errors to predict dynamic force at all sun planet and ring planet gear meshes. Flowchart shows the process of this research in figure 3.1. As mentioned in the preceding chapter, the gear fault may occur over time. Consequently, if a fault has not been previously recognized, it became a serious concern if the gear is failing or if it is failed. The cost of upkeep will be increased. There were a lot of explanations about how this research went from the start to the end in this chapter. It took a long time to find the best way to do this research. There are programs called MATLAB that can help us to do this variable analysis on gear faults. We can use this program to take a model simulation from this variable analysis. This chapter can also tell how well the vibration analysis works based on the method and the step of this research. Next, to figure out how vibration works, you need to use a MATLAB program to show how sound and vibration affect the part you choose. These parts are usually inside a transportation component. Those are the experimental setup. The configuration utilizes two distinct types of gears, spur gear and helical gear. Normal gear and fault gear with multiple combination of large and small gears. The result obtained was analyzed by vibration signal analysis with given parameters in MATLAB. The parameters used in this experiment include the machine's rotating speed, the sample rate, and the duration of the data collection period. Its purpose is to determine the difference in vibration between normal and defective gears. The data is taken during a 5-second period at a speed of 500, 1500 and 2000 rpm at which the machine must work. Spur gear and helical gear are utilized in this experiment. Spur gear monitoring of time domain frequency domain and Z-frag coefficient for this experiment. This experiment makes use of two sensors, sensor 1 and sensor 2. However, the time domain, frequency domain and Z-frag plots displayed below are from sensor 2 data alone. The particular sensor was chosen to represent the average outcome of the particular job. This is because the value of the data gathered from the two sensors are identical. As the figure shown below, the time domain and frequency domain experimental result for 4 different type speeds in large normal and small faults per gear situation. It shows that the vibration occur when the speed is increased. The time waveform data demonstrate the increase in transition component of the spur gear speed increase. Z-frag coefficient for the large normal and small faults per gear can be seen as the gear speed increase. The red and yellow dots in particular expand over the affect frequency. Additionally, all of the dots can be seen to split from one another at the high affect frequency relative to the annexed frequency. Helical gear monitoring also the same as we done for spur gear monitoring. The sensor 2 are chosen to take the data alone. In this figure below, the time domain and frequency domain experimental results for 4 discrete speeds in large normal and small normal helical gear condition has been shown. The spikes of the graph also increase when the speed increase. The time waveform data demonstrate the rise in transition component as the helical gear speed increase. Z-frag coefficient for the large normal and small normal helical gear is shown that as the gear speed increase, the green and yellow dots particularly expand over the affect frequency. Additionally, all of the dots can be seen split from one and another at the high affect frequency relative to the NX frequency. In terms of root mean square RMS, the figure below uses the data from sensor 2 to represent the average of the collected data. This is because the value of all the data collected from both sensors are identical. As for the trend depicted on the image, it indicates that the greater the running speed, the greater the RMS value. As the speed increases, the RMS value of both type of gear increase. Except spur gear condition RMS for large fault and small normal, because at the speed of 1500 rpm, the RMS is dropped from 1.3376 to 1.2172. The Z-frag coefficient obtained is plotted in figure below for each speed between 500 and 2000 rpm for spur gear condition. For speed between 500 to 1000 rpm, the Z-frag coefficient is nearly constant across all the conditions. The Z-frag fluctuation is illustrated for the large fault and small fault, and large fault small normal. This could be a result of the spur gear state being unstable. This is also suggested by the fact that the Z-frag coefficient increased significantly from 1000 to 2000 rpm. The Z-frag coefficient obtained is plotted in figure below for each speed between 500 and 2000 rpm for helical gear condition. For speed between 500 and 1000 rpm, the Z-frag coefficient is nearly constant across all the conditions. The Z-frag fluctuation is illustrated for the large fault and small fault only. This could be the result of the helical gear state being unstable. This is also suggested by the fact that the Z-frag coefficient increased significantly from 1000 to 2000 rpm. R square is the statistical measure that indicates how near the data is to be fitted to polynomial regression line. It's also known as a coefficient of determination, or in the case of multiple regression, the coefficient of multiple determination. Figure below shows that the data collected from the each speed, RPM and Z-frag is used to make a comparison by predicting the statistical method. The polynomial regression has a R-square value of 0.999, which is higher on large normal and small fault spur gear condition, because speed increased significantly on constant gear vibration at spur gear condition. Due to the fact that R-square value exceeds 0.9, the data collected and analysis performed can be considered reliable in terms of predicting the outcome of the spur gear vibration. Figure shows that the data collected from the each speed, RPM and Z-frag is used to make a comparison by predict the statistical method. The polynomial regression has a R-square value of 0.999, which is higher on large normal and small normal helical gear condition, because speed increased significantly on constant gear vibration. Due to the fact that R-square value exceeds 0.9, the data collected and analysis performed can be considered reliable in terms of predicting the outcome of helical gear vibration. Based on the distribution result from figure below, it can be seen that speed of 500 rpm and 1000 rpm have been closest accuracy among the other type of spur gear speed, indicates an accurate distribution. The next speed of 1500 rpm and 2000 rpm, which is of a substantially lesser accuracy than the earlier distribution speed. Based on the distribution result from figures below shows, it can be seen that speed of 500, 1000 rpm and 1500 rpm have been closest accuracy among other type of helical gear speed, indicates an accurate distribution. The next speed are 2000 rpm, which have a substantially lesser accuracy than the earlier distribution speeds. The primary goal for this research has been achieved, and it can also aid in the better understanding of the verification process of vibration analysis through the use of statistical methods, as well as better understanding of the approach vibration signal analysis in the experiment, which are both beneficial. For the recommendation on this study, other varieties of gear or many more combination of fault and normal gear can be employed to acquire a better understanding of vibration signal analysis, VSA. For instance, it can make use of bevel gears, warm gears and rag gear to aid an analysis comprehensions.